All right, next up we got Sarah Logsdon to talk to us about the NEID instrument. And let's see.
Can everyone hear me? Is this on? Can you hear me in the back? Yep, awesome. Thanks, Jada. I guess I should start while the slide is coming up, talking a little bit about the name of this instrument. The instrument looks like NEID, N-E-I-D, but it is actually pronounced NEID, and that is definitely my poor white person's pronunciation. This is a Thana Otham word, and Kitt Peak is actually on the Thana Otham land. NEID is not an acronym. It means to see, and telescope in Otham is actually tool for seeing stars. So part of the word for telescope is actually NEID as well, NEID could. So yeah, so I'll be talking today. We just heard about a new instrument concept, but I think a lot about NEID as the NEID instrument scientist and how we can continue to grow NEID, how we can keep NEID flexible to do all sorts of exciting science, and that's what I'm going to talk to you a little bit about today, thinking a little bit about the Q and then the wide variety of science cases we're doing now, and then maybe what is next. I talked a little bit about NEID being an Otham word, so I wanted to take a moment and acknowledge the fact that NEID is at the Wind Telescope, which is at Kitt Peak National Observatory, which some of you got to see yesterday. Thank you so much for coming up. Kitt Peak is also known as Yoakum Duag, which is the Otham for roughly translated into Manzanita Shrub Mountain. Astronomers like me are incredibly honored to be permitted to conduct our scientific research at Kitt Peak. This is a sacred mountain to the Otham located in the homelands of the Shuktwok district. We honor their past, present, and future generations of Otham who have lived in that area for time immemorial and will forever call it home. So here's NEID in a quick glance. I call this the spec sheet with no pun intended. Like I said, NEID is at the Wind Telescope. It's a 3.5-meter telescope. Steph was telling us how we needed really broad wavelength coverage and high spectral resolution, and NEID gives us both of those things. It basically covers the entire wavelength or optical wavelength range in one shot from 380 to 930 nanometers at very high spectral resolution, R of 115,000 in our high resolution mode. This is a radial velocity spectrograph, so we're designed to measure masses of planets around sun-like stars. That means that I talk a lot in terms of instrumental radial velocity precision and on-sky radial velocity precision. So if we're considering a single instrument measurement precision for NEID, we're doing better than about 30 centimeters per second. And as Suvrath told us a few days ago, our goal is to figure out how do we push towards that Earth-like planet around that sun-like star. That's a 9 centimeter per second signal. We've been in science operations since the summer of 2021, so we're starting year 5 now, which is super exciting. We are Q scheduled, so we're going to talk a lot about Q in this talk. We are currently 70 to 80% of the Wind Telescope time, so lots of uptime for NEID. NEID is publicly available. I'm sorry that we're 2 days late on the Noir Lab call for proposals, but if you think about an exciting science case today, please come talk to me because we have another call coming up in March. NEID is also available to the Wind partners through their institutional time. I should note that the public time is through a program called NN Explore. That's a joint program between NASA and the National Science Foundation for characterizing and validating exoplanets and studying their host stars. So Q, I think that NEID has 4 key building blocks of a Q, but before I talk about that, we should talk about why a Q. This is really necessitated by the exoplanet science. If you're trying to measure a mass of an exoplanet, you want as high of cadence observations as you can get. You're not sitting on the target all night long unless you're observing a transit. You really want a visit here and a visit there as much as you can throughout the semester and the year. So there's also a constraint on NEID's Q that NEID has to be scheduled such that it is off sky no more than 3 nights in a row. So NEID is keeping really busy. So let's talk about those key building blocks. This is an observability-based scheduling. That means that programs are still scientifically ranked by attack, but then they're assigned Q priorities not based on their science alone, but also based on how often you can actually visit that target. So we have 5 Q priority levels, and P0 is for your most highly time sensitive, and P4 is for your very time insensitive programs that can be done in poor weather conditions. We have to have real-time agility. That means at any point in the semester, a PI has to be able to go into their program and change lots of things. They can define a new observation or a new target. They can pause observations. They can change the number of visits. They can change exposure times, really almost about anything. And that also means we have to empower our observers to be flexible and agile as well. That means that they can add or remove targets or a schedule for the night to respond to condition changes. They can actually rerun the scheduler in the middle of the night. This sometimes is really great if another instrument has a problem at the observatory because they're there. We can turn to NEID and NEID can start observing and take advantage of that. They can also reprioritize our calibrators based on scientific needs and calibrator availability. Communication is key. We have talked a lot about how do we take the human out of the loop, and we've discovered that we can't take the human out of the loop entirely. We have a NEID Q coordinator and myself that work tirelessly in collaboration with the PIs to vet and check their observations, sometimes to get a new exciting target on the schedule quickly, to vet time accounting, really just anything to make sure that the communication is flowing. We also do that with each other and between day and night staff to make sure that the process is seamless. And we also need fast turnaround. That means the data need to be available quickly. NEID data is transferred off the mountain twice a day and reduced at the NEID NEID archive within 24 hours of receipt, so that PIs can almost in real time see their data and make those rapid, agile changes. How is our queue working? Thank you. I really like this slide from Arvind Gupta, who is in the back of the room. He is a Nawar Lab postdoctoral fellow and a member of the NEID instrument and science teams. This is a long-term 5-year survey called NETS, looking for Earth-like planets around quiet RV stars. What you're seeing here is a lot of dots, but each row is a target in the NETS survey, and the colors respond to observations at different priority levels from P0 to P2. And this is Arvind's model of what our survey strategy for NETS should look like in a perfect world. And this is what it actually looked like in the first 2 years of the survey. So let me do a quick bounce. I would say we're doing pretty good. Our queue is working as we expect. It's not perfect, but the patterns are very similar. I'm going to fast forward a little bit because I'm talking too slow. Let's talk about some science. So NEID does a lot of science. You're probably not surprised to learn that it does a lot of exoplanet science because that's what it was designed to do. It also spends a lot of time thinking about stellar activity, which is our tallest noise pole for RV science. So there's tons of stellar science that NEID is doing. We actually have a little solar feed. We're observing the sun about 300 spectra every clear day, and that data is publicly available immediately. So if you want to go to the NEID NEXI archive, you can get 300 spectra from a couple of days ago of the sun and start playing with it. We do the same thing with some RV quiet standard stars every night that NEID is on sky. We also provide tons of stellar activity indicators as part of our automatic data reduction pipeline. So here's a nice figure from Jacob Lund of our calcium H and K data. We also do fun, unexpected things with our stellar data. This is a nice science experiment that is being analyzed by a graduate student at Penn State, Elizabeth Gonzalez, actually of the October 2023 solar eclipse. So this is the moon passing in front of the sun. And what you're seeing here in the figure is a very nice Rosner-McLaughlin curve. So the moon is preferentially blocking red-shifted and blue-shifted light. So the spectrum from the sun is blue-shifted and then red-shifted. This is scientifically really interesting because this can tell us a lot about what is happening with the stellar activity of the sun. It's really powerful probing granulation, for example. So what you're seeing in the residuals are 3 models that Elizabeth has applied to the data, assuming that there is no granulation, with granulation on and off. And the red is with granulation on, and you can see we're fitting the data much better if we're assuming that there is convective blue shift happening in the sun, which we know is happening. So I don't have time to talk about the exoplanets, but we've had 2 excellent posters by Arvind Gupta and Shubham Kanodia, as well as a great talk from Sue Roth earlier in the week about our Earth-sized planet that was found in the habitable zone of its star. I also, before I leave, solar systems in context, we have a pilot study being run right now by Dan Lee at Noir Lab looking at what NEID can do in terms of measuring asteroid reflectance spectra. We've got a lot of great talks this morning from experts in this field. This is definitely very preliminary. One of the spectra, the red data is NEID, match the Gaia data beautifully. And the other one, we've got some systematics going on here, and we're still trying to understand whether those are physical systematics or something with our calibration. So stay tuned, but lots is going on with NEID. I will leave my summary slide up with links to learn more about NEID or to email me and take any questions.
Awesome. Thank you very much.
Yeah.
I have time for question. But before we do, is Noah Asano here? Oh, we're at the shop. Online now. Excellent. Okay,
Hello.
great. No, you're good. Thank you. Any questions for our speaker?
Yeah, so the NEID for high resolution case, how sensitive, I mean, how faint can you actually have it tried? And then, so because it's the calibration is taken at the same time, that's very stable, right? So the accuracy will be.
Yes, NEID is incredibly stable. On our RV standards, we have gotten less than 1 meter per second sensitivity over 4 years on some of the most quiet, most stable stars. And to your question about magnitudes, so the high resolution mode was originally designed to go to V of 12, though we've had a couple of folks really successful in assuming pristine conditions down to about 15.5, 16. But that's quite a challenge, and we really need excellent seeing and no clouds. Yeah.
Great. Any other questions for our speaker?
Thank you.
All right, well, thank you very much. And let's thank our speaker again.